Hello everyone, we start chapter 4, which is about network layers. The goal of this chapter is to understand principles behind network layer services like um, forwarding and routing. Also, we talk about different network layer service models, and we'll discuss how a router works and how routing algorithms can find the best path for data transfer in a network, and also we'll talk about broadcasting and multicasting using IP in the internet. So we first see an introduction to chapter 4. As I said before, network layer is the third layer in the layered approach of studying computer networks. So far, we have talked about the application layer and the transport layer, which are the fifth and fourth layers. So, in this chapter, we are going to discuss the network layer, which is the third one, and it is one layer above the data link layer and two layers above the physical layer. If you remember, the application layer and the transport layer are in the end systems. So, for example, if this is the schematic view of a network, uh, only the end systems like this one and this one have the application layer and the transport layer. All other devices, including the routers, have the other three layers: network layer, data link layer, and physical layer. But the important point here is the network core devices like routers do not have the application layer or transport layer, which means that they don't run the application layer protocols or transport layer protocols like TCP and IP, like TCP and UDP. Because in the routers there is no need to run the fourth and fifth layer protocols. So when a packet is sent from a source like this to a destination like this one, uh, the application data first is encapsulated to a data segment for the transport layer, and then that segment in the transport layer will be encapsulated in a datagram for the third layer, and then the datagram in the third layer will be added by some header of the data link layer, and then it will be passed to the physical layer. And then in the physical layer of the source, the data is transferred to all of these routers so that it finally reaches to the destination. And in the destination, we first extract the data link layer packet, and then that packet will be used in the network layer so that we can extract the datagram in the third layer, and then that datagram is used to extract the packet of the transport layer, and finally the packet in the transport layer will be used to extract the data that the application layer in the destination wants to use. Network layer has two key functionalities. One is called forwarding, the other is routing. Forwarding means the packets are transferred from one router to another router. Or we can say forwarding means move packets from router's input to the appropriate router output. However, routing is the process of finding the best path for data packets to be transferred through the network. So routing determines the route taken by packets from source to destination, and to do the routing we need to run some algorithms called routing algorithms. However, in forwarding, all we need to do is to move packets from the input port of a router to the appropriate output port of the router. So if you want to see an analogy, routing is like process of planning a trip from source to destination. However, forwarding is like process of getting through a single interchange. In order to find out more about the difference between routing and forwarding, consider this figure. In this figure, we will see a router here that wants to forward a packet that arrives at its input port. So let's assume that the packet that arrives at the input port of this router has the address of 0111. And this router has a table called forwarding table, local forwarding table, which maps every header value to the appropriate output link. So for example, this table says if the address or the header value of an arriving packet is 0100, forward that packet to the third output link. If the header value is 0101, then forward the packet to the output link number 2, and if the header value is 0111, then forward the packet to output link number 2, and finally if the header value is 1001, then forward the packet to the output link 1. So as you see, there are 4 rows in this forwarding table, and since the value of the arriving packet shown in this picture is 0111, therefore it has to be forwarded to the second output port, which is this one, and then after this packet is forwarded through this link, it arrives in this router, and again this router has its own forwarding table, and this forwarding table specifies which output link the arriving packet should be forwarded to, and this process will continue on different routers until the packet arrives in its designated destination. So this forwarding table does the job of forwarding a packet. However, we need to run a routing algorithm to fill out this table and write appropriate output links for each header value. So the routing algorithm determines end-to-end path through the network. However, the forwarding table determines local forwarding and at a single router. Similar to what we had for TCP connections, here in the third layer we can also set up a connection. To do this, we have to ask the end systems to establish a virtual connection among themselves before datagrams flow between from one host to another. However, the connection in the third layer, in the network layer, is different from the transport layer. Why? Because in the transport layer, the connection was among 2 processes. However, in the network layer, the virtual connection is between 2 hosts. Sometimes this virtual connection is also called virtual circuit. In the network layer, we have different kind of services that a datagram can enjoy, or a flow of datagrams can enjoy. For example, a single datagram can be the delivery of a single datagram can be guaranteed by the network layer protocols, or we can guarantee the delivery of a single datagram within, for example, 40 millisecond delay. However, we also have some services for a flow of datagrams. For example, there are some network layer protocols that guarantee the in-order datagram delivery. However, if you remember, in the internet, we don't have such service, and therefore we need to use TCP to make sure that the data is delivered in order, not out of order. And also, some of the network layer protocols can provide the service of guaranteed minimum bandwidth of a flow of datagrams. There are multiple network architectures in the third layer. For example, the internet protocol for the third layer network is one of them, and ATM is another network architecture. IP, or Internet Network Protocol, provides some services like best effort service, which means it does its best. It does its best to deliver data from source to destination. However, it doesn't guarantee the bandwidth. It doesn't guarantee data loss. It doesn't guarantee or in order delivery, and it doesn't guarantee the time that it takes. The minimum time, the maximum time that it takes for a packet to arrive at the destination. Also, it doesn't guarantee, it doesn't have any congestion feedback. However, there are some other network architectures, for example, ATM with service model CBR, which is constant bit ratio, which guarantees the loss and guarantees in order delivery and guarantees a maximum time for a packet to arrive at its destination. And there are, some other service models like variable bitrate or available bitrate that also guarantee some of these parameters. And for example, ABR, available bitrate, has a congestion feedback, which makes this service model guarantee the bandwidth. It guarantees a minimum bandwidth. But in this chapter, we focus on IP, the Internet Protocol, that doesn't guarantee any of these three items. In the rest of the chapter, we'll talk about virtual circuit and how they're different from datagram networks. So if we want to compare datagram with virtual circuit, datagram is a connectionless service in the third layer, in the network layer. However, virtual circuit is a connection-oriented network layer service. So it's similar to the difference between TCP and UDP for the transport layer services. TCP is a connection-oriented protocol. However, UDP is connectionless. However, they're different from TCP and UDP because in the third layer, the service is between two hosts. The connection is between two hosts. However, in the fourth layer, the connection is between two processes. And also, in the fourth layer, we had the option of choosing either TCP or UDP in the same network. However, for the third layer protocols, we should either use virtual circuit or datagram network. We cannot use both of them because if we want to switch from one protocol to another protocol, we have to change the network core completely, and it's not possible to choose to switch between virtual circuit and datagram network on a single network. And also, the implementation of TCP and UDP happens in the end system. However, the implementation of datagram networks and virtual circuit networks will happen in the network core, which includes routers. So a virtual circuit behaves like a telephone circuit. Between source and destination, there is a virtual path of data in which the source can send data to the destination on a reserved path, and no other connection can use that path. It's similar to a network circuit. However, to enjoy such service, you have to set up before the data can flow. You have to set up the connection before the data can flow, and also you have to tear down the connection after you finish sending data from source to destination. Also, we must, the routers must remember the state of packets in a connection, and also each packet carries a virtual circuit identifier, which we'll talk about later in the next slides. And also, virtual circuit is not very efficient, because when two end systems reserve a connection, they're not using that connection 100% of the time. And for example, if they use it only 20% of the time, then the resources that is reserved are wasted for 80% of the time. So it's not a very, very efficient performance wise. However, it is convenient for the end systems, and also it may guarantee some bandwidth. In order to implement a virtual circuit, we should have a path between source and destination, and we should specify one number, which we call it VC number, for each of the links along the path. And also the forwarding tables in the routers along the path should remember these VC numbers. Here is an example of implementing a virtual circuit. This is the VC forwarding table that is stored in this router. So as you see, there's a connection established between this host and this host, which contains which goes through two routers, this router and this router, and goes through three links, this one, and this one. As I said before, each link has a VC number. For example, this link has VC number 12, this link has VC number 22, and this link has VC number 32. And also, please note that this link may participate in other connections. However, it should have a different VC number than 22 in other connections. Why? Because we should distinguish this connection from other connections. And if you look at this forwarding table in the northwest router, you can see what kind of information the forwarding table has to remember. For example, it remembers that if data comes from interface number 1 with incoming virtual circuit number 12, it has to be forwarded to outgoing interface number 3, and the outgoing virtual circuit should be set to 22. So as you see, the forwarding table for virtual circuit is much larger than what we saw in the beginning of the chapter, which was for datagram networks, not virtual circuits. So virtual circuit routers maintain connection state information. However, the routers in datagram networks are much simpler and has less complexity. There are some signaling protocols that are exchanged between two end systems when a virtual circuit is going to be established. For example, at the beginning, the first end system initials a call to the second end system, and the second end system accepts the call, and then the first end system creates the connection, and then the first end system starts flowing data toward the second end system on the same path that is created, and then the data is received by the second end system. As you see in this slide, the datagram networks are different from virtual circuits. For example, if this end system wants to send some data to the other end system, it doesn't need to set up a connection at the beginning of the session, and it doesn't need to set up a path between source and destination. All it needs to do is forward these packets to the immediate router connected to the end system, and the end system, the router can take care of forwarding the packet to the appropriate output ports, so that it eventually reaches to the designated destination, and packets are forwarded using the destination host address that is determined by the header of each packet. Also, the routers have much simpler functionality, and they don't need to remember any state about end-to-end connections. Instead, the end-to-end the end systems are the ones who remember all the information about the connection among themselves, and this connection setup happens in the fourth layer, in the transport layer. If you remember, in the TCP, the end system had to establish a connection in the fourth layer before starting a connection. So everything about connection setup will happen on the end systems, not in the network core. So that's the difference between datagram networks and virtual circuits, because if you remember, in the virtual circuits, the routers were the one who had to remember the state of a connection between two end systems. So in the next slide, we'll talk about how the forwarding table of a router looks like in a datagram network. If you remember, the IP address is a 32-bit integer, and there we have 4 billion different IP addresses. So rather than listing all the individual destination addresses in a forwarding table, we have to write a range of addresses in a range of address in each row. For example, in the first row, we have a range of addresses that is different from the range of addresses in the second row. And for each row, we specify the appropriate output link, and this table can help the router to forward any data packet that is arrived to its input port. Here is an example of datagram forwarding tables. As you see, in each row we have a range of IP addresses. For example, in the first row we have this range, all the IP addresses that are greater than or equal to this address and are less than or equal to this address should be forwarded to link interface number 0, and also all the packets that are between these two addresses should be forwarded to the link interface number 1. All IP addresses between these two addresses should be forwarded to link interface number 2, and in other cases the packet should be forwarded to number 3. So obviously we have to have a default case like this, otherwise we cannot forward some data packets with some specific addresses. So we have to have some default case. So I showed you one way of showing the address ranges in the forwarding table. Here is another way of showing address ranges in the forwarding table. Look at this number. In this number, some digits are specified. As you see, the first 21 digits are specified. However, the next 11 digits are not specified, and they are replaced by stars. That star means each of these stars can be replaced by either 0 or 1. So that will create a range of addresses for this row of the forwarding table. So any IP address that has the first 21 digits like what we have here should be matched into the first row of this forwarding table, and therefore it should be forwarded to the link interface number 0. And if the first 24 digits of a IP address matches these numbers, then that packet should be forwarded to link interface number 1. And if the IP address of a packet starts with these digits, no matter what the other digits are, it should be forwarded to link interface number 2, and otherwise it should the packet should be forwarded to link interface number 3. So for example, if the IP address starts with 1100100000001010, then these 21 digits are the same as what we have here. Therefore, the first packet has to be forwarded to link interface 0. How about the second one? In the second one, the digits matches both the second and third address ranges that we have here. So as you see, the second address range has 24 digits at the beginning, and all of these 24 digits matches what we have here in this address. However, the first 21 digits of this address matches the IP address range that we have in this row. Okay, so in other words, this address matches both the second address range and third address range. In such situations, the tiebreaker would be longest prefix matching criteria. What does it mean? It means that the address range that can match longer prefix of the IP address should be used for forwarding the packet. In this case, since the second row matches up to 24 bits of the address that we have, should be used for this packet. So this packet should be forwarded into interface number 1, because the prefix because 24 digits of its prefix matches the address that we have. However, in the third row, only 21 digits of the prefix matches the address that we had. So we have to use the longer one, which is the second row. Therefore, the second IP address should be forwarded to link interface number 1. So in summary, we can say datagram networks have simpler inside network, which have similar core networks, and more complicated network edges, or more complicated end systems, because the end systems in datagram networks like internet are computers. However, in VC networks, in virtual circuit networks, the the network cores are more complicated and the end systems are simpler because they are dumber. The end system are usually telephones, and telephone has no computational power. It's a dumb device. In the next slide, we talk about what's inside a router. So a router consists of some input ports, some output ports, and one high-speed switching fabric, and a routing processor which enforces the routing algorithm, which specifies which input port should be forwarded to which output port. The forwarding tables computed by the routing processor is pushed into input ports, and the input ports are the ones who decide where to forward every packet arrived at the router. Here is a more detailed structure of an input port in a router. As you see, there are three different black boxes here. The first one is the line termination. So when a link is which is connected to the router reaches to a router, it will come here, and here we have the line termination, and then the data that arrives here goes to the next black box, which runs the link layer protocols. And in this link layer protocol, we, for example, run the Ethernet protocol, and we will see more details about this in chapter 5. And the link layer protocol extracts the data and forward the data to the next table, the next block, which is the lookup forwarding block. In this block, the datagram destination address, which is specified in the header of the network layer protocol, is used for the purpose of forwarding. So based on the destination IP address, the forwarding table in this box decides which output port the data should be forwarded to. And also, if the datagrams arrive faster than forwarding rate into switch fabric, then the packets have to be queued here, have to be buffered here, and they should go through a queue. Why? Because the arrival rate may be faster than the forwarding rate in to switch fabrics. We have three different types of switching fabrics. One is this one, which is like a memory. The input ports write their incoming data to the memory, and then the outgoing ports will simply read from that memory. We have one other type of switching fabric, which is a bus. It's a mutual bus, it's a shared bus with a specific capacity, and all of these input ports put their data in the shared bus, and the outgoing ports, the output ports, will pick up their own data packets from the bus that is shared among all of them. There is one more type of switching fabric which is faster than the others, which we call it crossbar. It's a grid of connections, and for every pair of input port and output port, there is a specific path that connects the input port to the output port. For example, here the first input port can be connected to the second output port in this through this path. If you want to connect the third input port to the third output port, you have to use this path. So there is one single path for every pair of input and output ports. Memory in switching fabric is used in the first generation of routers, this type of switching fabric is very slow, and the speed is limited by memory bandwidth. When we use bus as a switching fabric, then the switching speed is limited by bus bandwidth. For example, a 32 gigabit per second bus is a sufficient speed for access and enterprise routers. And as I said, here is the third type of switching fabrics that is faster than the previous two types. And also here is the details about the output port of a router. As you see in the first step, we may have to buffer some outgoing packets because the rate in which the data comes from switching fabric to the buffer may be faster than the outgoing. Maybe faster than um, the bandwidth of this or transmission rate of this link. Therefore, we have to buffer data before forwarding it, and the buffering and queuing datagrams are not very simple. Sometimes we have to have some priority for some packets. Some packets may be queued maybe queued later, but should be forwarded earlier. So the queue here is not a first in first out queue necessarily. It's a priority queue, and some datagrams may have higher priority. We'll talk about this scheduling datagrams later. Again, as I said before, if the rate of data flow that comes to a outgoing port is faster than the bandwidth of the transmission rate of this outgoing links, then we may have some queuing delay or even loss due to output port buffer overflow. To find an estimation of how much data is buffered in a network, you can multiply the RTT, the round trip time, by the link capacity. So RTT times C is a rule of thumb for average buffering calculation. And then whenever you have n flows in the network, and the throughput equal to C, or the capacity of the link equal to C, then you can estimate the average buffering by multiplying RTT by C and then divide it by the square root of number of flows in the network. As I said, not only we have queuing in the outgoing ports, we may have queuing in the input ports. Here is a scenario in which we have input port queuing. These two red packets want to be forwarded to this outgoing link, but at a single time the switch fabric can only forward one of them. So if this is forwarded first, this has to stay in the input port queue of this in the queue of this input port. And also we may have some other scenarios in which we may have to queue packets in an input port. For example, here the green and the red packets arrive in this input port of the router, but since this packet is getting forwarded to the output link that you see here, the green one has to wait because the red one blocks it. So it's called head of the line blocking. The green one cannot be forwarded by the switch fabric to this output port because the red one is blocking here, and the red one is getting forwarded, and the switch fabric is busy forwarding the red one. Next, we talk about the internet protocol, which we call it IP. So In the Internet Network Protocol, we have multiple protocols. RIP, OSPF, and BGP are used for path selections and running routing algorithms. Then, these routing protocols will fill out the forwarding tables in a router, and also the network layer runs the IP protocol, which is in charge of addressing conventions, datagram formats, and packet handling conventions. Also, we have some other protocols like ICMP, which are in charge of error reporting and router signaling. Similar to what we had for TCP headers and UDP headers, the IP datagram has also a header with a specific format. For example, here you can see there are some fields in the IP datagram header like version number or header length, the total length, the IP address, the 32-bit IP address of the source, and the 32-bit IP address of the destination. And there are 20 bytes in the TCP header, and there are 20 more bytes in the header of IP. So we have an overhead of 40 bytes that will be added to the application data by both TCP and IP. Every link in network has a maximum transfer size, which we call it MTU, and if the IP datagrams are very large and larger than MTU, we need to divide them into smaller pieces so that we can transfer them on a link. For example, a datagram that you see is in this router can move on this can be transferred on this link, because this link has a large enough MTU that can handle this large datagram. However, the next link on the path does not have as large MTU as the previous link had. So here this router has to fragment the datagram into 3 smaller pieces so that it can transfer it over this link. And this link has MTU of at least this size, the MTU equal or greater than the size of these small pieces. Therefore, we don't fragment it anymore. And then finally, the 3 fragmented datagrams will be delivered to the destination. And finally, in the destination, we have to reassemble the fragmented datagrams to reconstruct the one large datagram that we had originally. Here is a numerical example of IP fragmentation and reassembly. Let's assume that the original datagram has 4,000 bytes in total, including the header. So after deducting the 20 bytes of IP header, we will get to the number of 3,980 bytes for the total data that the original datagram has. But let's assume that this datagram is going to go through a link with the MTU of 1500 bytes. So we cannot transfer this large datagram in a link of 1500 bytes. Therefore, the IP has to divide this this large datagram into smaller pieces so that they can fit into that link. Since MTU is 1500 bytes, it means that we can only have 1480 bytes in data field for each of the smaller datagrams. So out of those 3980 bytes of data that we have in the original datagram, we can have 2 times 1480 bytes into a smaller datagrams, and another 1020 bytes in the third datagram. So as you see, this large datagram has been divided into two datagrams of size 1500. Why the size of 1500? Because it has 20 bytes of header and 1480 bytes of data field, and the last one, the third one, has only 1020 bytes of data plus 20 bytes of bytes of header, which makes the total length of the last datagram equal to 1040 bytes. Please note that every smaller datagram has an offset. The offset is used to make sure that in the reassembly process we merge all the smaller datagrams in order to reconstruct the original datagram appropriately. So the offset is calculated by the number of bytes divided by 8. For example, the offset of the second datagram should be 1480 because the first datagram has 1480 bytes, but here we have to divide it by 8 because, as I said, the offset is calculated by the number of bytes divided by 8. So here we write 185 for the offset of the second datagram, and the offset of the third datagram is twice the offset of the second one, which is 370. Next, we talk about IP4 addressing. Every end system in a computer network must have an address, which we call it IP address. The IP address has 32 bits, which can be represented by 4 integers between 0 and 255. For example, this sequence of 32 bits can be divided into 4 equal pieces. Each piece can be represented as a integer between 0 and 255, which is 2 to the power 8 minus 1. And not only the end systems are addressed by the IP address, but the interfaces of every router has to have an IP address. For example, here this router has 3 interfaces. Each one of them has a different IP address. The interface in the router is connected to these end system via a device that is called a switch. We'll talk about switches in the next chapter. So for now, you don't need to worry about how one interface is connected to another. Every computer network can be divided into smaller subnetworks, which we call them subnets. In this figure, we have 3 subnets. This is one of them, this is the second one, and this is the third one. As you see, the router connects these 3 subnets together. It's important to notice that if the end hosts in a subnet want to communicate, they don't need to use the router, but if 2 end systems in 2 different subnets want to communicate, they have to use router to send their message. As you see in this figure, the IP addresses of all the elements in a subnet has 24 bytes, 24 bits of mutual prefix. So, for example, these three IP addresses, they all start with 222.1.3, which represent 24 bits. The only difference between these three IP addresses are the last 8 bytes, the last eight bits of their addresses. Therefore, you can address this subnet as 223.130/24. The 24 is called the subnet mask, which specifies the subnet part of an IP address. You can see similar subnet addresses for these two. This one has 223.110/24 subnet address, and this one has 223.1.2.0/24 subnet address. As another example, you can count the number of subsets in this figure. As you see, we have 1, 2, 3, 4, 5, and 6 different subnets. So even a subnet can be as small as only one link, like what you see here. In summary, you can divide an IP address into two different parts. The left hand side part, the first part is called the subnet part, and the second part is called the host part. The length of the subnet part is called subnet mask and is separated from the IP address with a slash character. The length of the host part can be calculated as 32 minus the subnet mask. In this example, the host part has a length of 9 bits, which makes the subnet to have the capacity of up to 2 to the power 9 hosts, which is equal to 512 different hosts in one subnet. A host can get an IP either by the system admin or it can get an IP address dynamically through an app layer protocol called Dynamic Host Configuration Protocol, or DHCP. This protocol is plug and play, which means that you don't need to set up anything. As soon as, for example, your mobile device is connected to internet, it can get an IP dynamically using the DHCP protocol. The goal of DHCP is to allow hosts to dynamically obtain its IP address from the network server. So the first step of DHCP is that the host that wants to get an IP broadcasts DHCP discover message, and then the DHCP server, if it's nearby the host, will respond with a DHCP offer message which contains an IP address, and then the host requests to have that IP address from the server, and then the server acknowledges the request of the host. Here is a scenario in which DHCP client asks DHCP server to have a IP address. So let's assume that this client just joins this subnet in the network, and then as soon as it arrives, it asks the DHCP server to have an IP address, and then the DHCP server responds with an available IP address, and then after clients ask that whether it can have the IP address, DHCP responds yes and acknowledges the request of the client, and the client can have an IP address like other end system in this subnet. Here you can see a simplified scenario. First, the arriving client broadcasts a request to see whether there is a DHCP server or not, and then the DHCP responds with an IP address that the client can use, and then the client notifies the server that the client is going to use the IP address, and then DHCP server acknowledges the comment of client. DHCP can not only returns the IP address to a newly arrived client, but it also gives the client the name and IP address of the DNS server and also the network mask. Moreover, the client can find out the first hop router, the address of the first hop router by using DHCP protocol. As you see in this figure, DHCP is a protocol in the application layer that uses UDP for the fourth layer, for the transport layer, and IP for the third layer, and Ethernet for the second layer, although it can use other protocol in the second layer, but in this example, Ethernet is used for the link layer protocol. Here you can see a more detailed client-server communication of DHCP protocol. Every internet service provider has a block of IP addresses. Some have more larger blocks. Some have smaller blocks. For example, in this numerical example, the ISP block has 4,000 4,096 different IP addresses in its block. The reason that it has 4,096 is because the subnet mask that the ISP's block have is 20. Therefore, 12 bits remains for addressing the host. Therefore, for 12 with 12 bits, we can address up to 4,096 different hosts in a subnet, and this ISP can serve like 8 organizations, and each organization can enjoy up to 512 different IP addresses. As you see, the subnet mask for each organization is 23. So we have 8 subnets with the subnet mask 23 inside the ISP's block. As you see in this schematic view of the network, there are 2 ISPs. This one is smaller than this one. The fly-by-night ISP has a subnet mask of 20, therefore it can handle up to 8 organizations with subnet mask of 23. However, ISPs are used is another ISP with subnet mask of 16. So when you have a subnet mask of 16, you can handle up to 2 to power 16 different IP addresses, which is 16 times more than what fly-by-night ISP can handle. There's a corporation called Internet Corporation for Assigned Names and Numbers with this web page address that can sell ISP blocks. Consider a router that connects this subnet, this local network, like a home network, to the rest of internet. This router can represent the whole local network by one single IP address that you see here, 138.76.29.7, which is the IP address of this interface of the router. All datagrams that are leaving from this local network would have the same single source NAT IP address. We call this NAT because NAT stands for Network Address Translation, and every uh, other host in the rest of internet that wants to communicate with the host inside this local network uses this IP address as the IP address of uh, destination, and uses different port numbers to distinguish between the hosts in this subnet. The motivation of network address translation is that some local networks can use just one IP address to connect with the rest of the world, and uh, sometimes you don't want or you cannot afford so many IP addresses for a local area network. That's why we use network address translation to use one single IP address of ISP for a whole local area network. Using network address translation can improve the security of a local area network because the other because other hosts in the internet don't know what the IP address of each host inside the local network is. They all see a single IP address for all the hosts in a local area network, and also another good thing about using network address translation is that you can change addresses of devices in local network without notifying outside world, and you can change ISP without changing addresses of devices in local network. To implement network address translation, the NAT router, the router that is responsible for network address translation, has to replace the source IP and port number of every outgoing datagram by the NAT IP address and a new port number for every outgoing datagram that wants to um, get out of the local area network and wants to reach to the other parts of the internet. And also that router has to remember every source IP address and port number to the NAT IP address and new port number translation pair, because uh, maybe later it wants to use them for the upcoming datagrams, and then every incoming datagram which has a NAT IP address and new port number has to be replaced by the source IP address and port number of the host in the NAT table. Here is a scenario that clarifies how network address translations work. Let's assume that this host in the local area network wants to communicate with a host with IP address 128, 119, 40, 188 with port number 80, and also assume that this host has an IP address of 10.0.0.1 inside the subnet with the port number of 3345. And then while the datagram coming out of this host wants to go over this router, the router will translate the IP and port number of that datagram to a new IP address and the port number. So the translation of this pair of IP and port number will be 138.76.29.7, which is the NAT IP, and 5001, which is a new port number for this host inside the local area network. And then as you see, after the datagram is coming out of this router, the source IP and port number will change to the one that is stored in the NAT translation table. And then when a reply comes out of the IP 128, 119, 40, 186, it when it reaches to the router again translates the destination's IP address and port number to the one that is stored in the NAT translation table, and this way inside the subnet we know that which host has to receive that message. In this case, it is the same host that sent the message, which is 10.0.0.1 and 3345. Since the port number has the length of 16 bits, a NAT router can handle up to 2 to the power 16, which is around 60,000 simultaneous connections with a single LAN side address. However, NAT is controversial and it violates the layered approach of computer networks, because the router should only process up to the third layer, but a NAT router has to change the port number. So this way we are violating the end-to-end argument. That's why in order to resolve the address shortage, it's better to use IPv6, which is 2 bytes longer than IPv4 addressing.